Well, hey everybody, welcome to lecture 9. Um, this lecture is going to be YouTube. I tried in the last lecture embedding the narration in the PowerPoint. It seemed to work, but I uploaded to Canvas and it used up about over half of the total disk space we have allocated. So, well, that was a bust. At any rate, we'll do it this way. So the point of this lecture is to talk about the ultrasonic sensing. Now for the next project, we're going to use that. We're going to make a system where it um, measures ultrasonically a distance and displays it on the LCD. All right, so this is the kind of the first half of that. Now, the first thing, let's talk a little bit about ultrasonic sensing. So, it's a common thing. It's what bats use. They make a little beep and then they listen for it. Torpedoes use it. That's the basis of sonar. By the way, that's the Mark 46 you see there on the right. By the way, in the sonar section, it's got some software I wrote. And then, of course, Arduinos use it. So in the kit that you got the other day, there's this little funny looking thing. I put a red circle around it. That's an ultrasonic sensor, and it's really fun on the Arduino because they mount it on a servo system. So in the software, you can actually move and point the ultrasonic sensor, independent of where the wheels are taking you. So, all right, so how does ultrasonic sensing work? Well, the concept is fairly simple. You need a speaker, and so you create a sound on the speaker, and then you need a microphone, and you listen for the sound to bounce back. And what you do is you measure the time from the time you created the sound to the time you hear the echo. And of course, these are very short amounts of time. These are in microseconds, so microseconds a millionth of a second. And what it is the delay, the time from you make the pulse to the time you hear it back. The equation is it's basically 2 times the time it takes times the speed of sound. Now that 2 is there because the sound travels to the target and then back, so it goes twice as far. So if there's something 5 inches away, the sound wave will travel 5 inches to it and 5 inches back. So that's why we have that factor of 2 in there. All right, so and it turns out to what's the speed of sound? Well, it turns out if it's an ideal gas, it's actually fairly easy to compute it. Now, I won't go into all the details. At some point, maybe in grad school, if you take a class with a title like compressible flow or supersonic flow, they'll drag you screaming through all these equations. But for now, I'm just going to present the equation. By the way, I mentioned compressible flow or supersonic flow just to blow your mind a little bit. Compressible flow is supersonic. They are actually, by definition, they are the same. So you may have thought, oh, compressible flow is this or that, and supersonic flow is something else. Pretty much you can define compressible flow in terms of either how the density changes or in terms of the Mach number. Basically, Mach number above about 0.8 is compressible flow. So anyway, you'll get more about that in another class. But at any rate, it turns out for an ideal gas, most of the terms cancel, and it's this. A is the speed of sound, and it's basically a constant times the square root of T, where T is the temperature. Now, it's got to be absolute temperature. So a 0T is the point at which molecular motion stops. So normally, the little parts inside the atom or kind of the molecules are all bouncing around. At absolute 0, nothing's bouncing around. So you've probably seen Kelvin somewhere in your studies where in metric units, 0 Kelvin is absolute 0. If you're wanting to do things in the British system, the imperial system, there's actually an equivalent which is called Rankine. So it's something like, I don't remember the exact, but it's something like absolute 0 is minus 460 degrees Rankine or something like that. At any rate, so it turns out if you for the purposes of the speed of sound, if you treat air as an ideal gas, it actually gives you some pretty good results. That's what we're going to do. In the world of compressible flow, that's usually what's done. And here's what it is then. In metric units or SI units, the A, speed of sound, is 20.05 times the square root of t. So A has the units of meters per second, T has the units of Kelvin. So at 25 degrees Celsius, there it is there in the equation, it's 246.2 meters per second. And now in the next line, what you see is, we multiply by 100 to convert the meters to centimeters. We divide by 1,000,000 to convert the seconds to microseconds. And there in the red box, you get 0.03462 centimeters per microsecond. Boy, those are odd units. I wonder why I put them in those units. Hold that thought, will you? Okay, so meanwhile, let's talk about the hardware. So this crazy looking thing, it looks like they're eyeballs. It's actually just two speakers and microphones kind of integrated. It comes with the Arduino. So on the left, that's the front. On the back, that's the right. And what you'll notice, there's 4 pins. You can see them. They're labeled on both sides of the board. You can kind of see my thumb there, my thumbnail, to kind of get a sense of the size. This thing, it's fairly small. But anyway, so you see those 4 pins at the bottom. So what's the story with those 4 pins? Well, they're labeled VCC. So what you do is you attach this to the 5 volts on your Arduino. There's one called trig, and what you do is attach this to one of the digital pins on the Arduino. You're going to configure that as an output. And so remember I said we're going to make a noise and then listen for it. So the idea is you set that high and that makes the noise, and you set it high for a little bit, set it low, and then on the echo, you listen back for when it echoes. And so with trig, you set that to an Arduino pin, a digital pin as an output. With echo, you set it to an Arduino pin as an input. And then for ground, well, you just attach that to the ground on the Arduino. All right, and so, everything I've said, that just from what I've said, that probably ought to be familiar by now. Let's suppose you're going to use pin 4 as a trigger and pin 5 as the echo. You're going to set up a variable that's for the pin and the trigger and the echo. And you're going to set the trigger to output and the echo to input. So hopefully that's seeming real familiar. You're going to do that in setup. So that should be second nature by this point. Now, what you're also going to do, and this part's going to be in your loop, where you're going to have a variable called, let's call it time in microseconds. And first what you do is you're going to make sure the trigger's low. So we're going to do a digital write to the trigger pin. We're going to make it go low. And typically what you see is people wait about 2 milliseconds. So delay goes 2 milliseconds. And, I'm usually kind of down on delay. Certainly if you're up in the 100 or 1,000 milliseconds, I'm definitely down on it. For 2 milliseconds, yeah, it's probably all right just to do it like this. You could do it with a state machine, but it'd have to be a pretty fast interrupt rate. Then what you do is you set the trigger high for 10 milliseconds. So digital write, trigger high. Then we delay for 10 more milliseconds, and then we do another digital write. We bring it low. So we just went bloop, bloop, and that square wave is the pulse that goes out. Now we've got some big news here. There's a function in Arduino, you see it at the bottom of the page here, called PulseIn. And what that does is that listens for a pulse to come back. So when you call it, if the specified pin, actually what I've told it is, for the echo pin, wait for it to go high. See what I wrote there? And it's going to return the time in microseconds. Microseconds. That's probably why I converted the speed of sound to be microseconds, centimeters per microseconds, because when you multiply, you'll get centimeters. Okay, so let's go to arduino.cc. Here's PulseIn, and here's kind of the description. You can read it for yourself. It's pretty much what I just said, and really whenever you're introduced to a new thing here, your gut reaction, your knee-jerk reaction ought to be, I'm going to go to arduino.cc/reference and read about whatever the command is. So here it is. Basically, it waits and returns the values in microseconds. All right, so then for computing the distance, we have a float here. I'm going to say it's distance in centimeters. And here's where the equation is. You just simply take the time in microseconds times that value we computed and divide by 2, right? Because it goes out and it comes back, so we divide by 2. Now, the caveat is, in my experience, this sensor, when you're close to about 3 centimeters, a little more than an inch, doesn't seem to work very well. And when you get about 30 centimeters away, that doesn't work well either. But in between, it's pretty good. And what I find is, if it's something like a ball or something round, that doesn't seem to work real well. But if you get like a book or even your hand, or, if you have like a box, where you have the sensor and you're bouncing off a box, that'll work really well. And it's actually surprisingly accurate. And what you do is you take your ruler and, preferably get one in centimeters, since this is all going to be in centimeters. And it's amazing. You can actually see, like, wow, that actually, works. Bear in mind, our equation or calculation for the speed of sound assumed a temperature. If you are in a very cold place in winter or a very hot place in summer, what you'll find is the measurement becomes inaccurate because the speed of sound changes as a function of temperature. At any rate, as a final note, here's kind of the end game. So for project 5, we're going to create a system that you see here. I put the ultrasonic sensor on the little breadboard. If you haven't looked thoroughly through Arduino box, we got the first one. There's the big one, you use that. There's also a little teeny breadboard. It works the same. It doesn't have the plus and minus on it, but it's still a breadboard. For this one, I put the sensor on one. I put the LCD on the other. There's actually some other stuff there. And you see I'm running it off the battery. I want us to do that to get familiar with that. But the whole deal is this is an ultrasonic distance sensor, where as you move things close and far, it will give the distance there on the LCD. So on the next lecture, I'm going to talk about how to use that LCD. But at any rate, that's it for now. The whole idea is we wanted to help you understand how to use the ultrasonic sensor. At any rate, thanks for listening. Hope everything's going well. Hope you don't have coronavirus, and we'll talk to you later.